Math 265A, Quest to College. I'm Joe Vasta, and we are covering Section 5.5, the Substitution Rule, or another name for that is change of variables. And we are going to now learn how to do antiderivatives of things that we wouldn't be able to do before. We might be able to do this if we multiply that out 40 times. But before we get into this, we are going to do something called change of variables, substitution rule. And we've already done that before, and hopefully you've done that before in other classes. Like we have this equation here, and this equation has an x minus 100 there and an x minus 100 there. Now, it's true that I could multiply this out, and I'm not going to do that, but I'm going to show you what you get if you multiply it out. If you multiplied it out, you'd get like an x squared minus 202x plus 10,197 equals 0. Then we would have to try to find two factors of 10,197 that would add to give you a negative 202. So this is not what we want to do. There is a better way of doing this problem, and the better way is to do a substitution. I'll call it a U-substitution. I'm going to replace each x minus 100 with a u. So u could go like this. U equals x minus 100. Basically what we're doing is we are tricking this problem into getting done. Tricking it into an easier problem. If u equals x minus 100, then this is a u squared minus 2 times u minus 3. This equals 0. Surely I can solve this one by factoring 3. Factors of 3 that subtract to give you a negative 2. I have u here, u there. 1, 3, minus on the 3, plus on the 1. And what I end up getting is u plus 1 equals 0. U minus 3 equals 0. U equals negative 1. U equals 3. I'm going to replace those u's with what they originally were. So we'll do that up here because I'm running out of space. This is x minus 100 equals negative 1. So what I did is I replaced this with that right there. And the other one becomes x minus 100 equals 3. So the first one gives me, I add 100 to both sides, I get x equals 99. And the second one, I add 100 to both sides, I get x equals 103. So my answers are 99, 103. I went ahead and I did a U substitution, was able to do a problem that was doable, and then came back and switched it back to that. That's what we're going to be doing with integration, except we're going to be doing calculus instead of just some algebra. So back to our original problem. We have something that looks like this. So we want to do a U substitution, and we take a look at this and say, well, what would we like letter U to be? And in this problem, so we'll just go ahead and look at this right here. We're going to replace that x squared plus 3 with a u. It's kind of like the last problem that I did where the stuff in the parenthesis gets replaced with a u. That's not always going to be the case. So let me go ahead and do this. I'll do this right here. Oh, there's this thing right here. I didn't say this. The book is going to tell you to use a table 5.6 for some of the problems. You can if you want, but I would highly recommend not doing that because they're going to get you into bad habits where you think you need a table to do things you do not need a table to do. So this is a bad thing they're telling you to do when you do the homework problems, and there are a lot of homework problems. Just evaluate. That's what we want you to do. Okay, so U equals x squared plus 3. So that's what we're going to do. So we're going to trade out all of our x's for u's. Now, I have a dx there, and I want to not have a dx there. So what I'm going to do is I'm going to take the derivative on both sides, and I'm going to use differentials. So the derivative of u is, I'm going to go du. This equals, and then on the right hand side I'm going to take the derivative of x squared plus 3, which is 2x dx. Now if that confuses you, maybe you could divide by dx and you see that du dx equals 2x. So you might be more used to that, but I'm breaking these guys up and putting the dx there. And now, look what I have. I have a 2x dx right there. And my original U substitution, I'm going to replace this x squared plus 3 with a u. So I have a u to the 40th du. Now, is this something that we can do? And the answer is yes. And so I'm going to go ahead and use the power rule. This is going to give me u to the 41 over 41 plus c. Now, lots of times people will do a u substitution and they will say, oh, there's my answer, and box it. The original question asked was written in terms of x's. So we're going to change this back to x's. When we do that, I go ahead and use this right here, u equals x squared plus 3. So this is x squared plus 3 to the 41 power, all over 41, plus c. And that is our answer there. We have now found the antiderivative of something that was very complicated to do, and we did a u substitution. Now we could check our answer, and I'll check the answer in green. This right here is our answer. Let's just check it by taking the derivative. If I took the derivative of this, look what I'm doing. I am doing the chain rule, where so I have the 1 over 41 out front, and let's go ahead and take the derivative. We have 41 x squared plus 3. This becomes to the 40th, and then we take the derivative of the inside, which happens to be 2x. Then the derivative of c is 0. The 41s cancel, and I end up getting the original problem, which is x squared plus 3 to the 40th times 2x. What I'm going to do is I'm going to show you another way of thinking about this problem. And I'll do this on a few problems. This will work a lot of the times. I'm going to redo this problem. The thing that I want to point out here is that U substitution, I'll write it here, U substitution, that's this method, the substitution rule. U sub is really the reverse chain rule. Remember when you first learned the chain rule? That's what we did right here. We did the chain rule. We, the 41 jumped in front, and we put a 40 up there. And then it wasn't magically, but I'll just say magically. Magically, the derivative of this inside appears. So when you're doing U sub, this was the derivative of this inside here. It doesn't appear because we're doing the reverse chain rule, it disappears. So some of you might not want to do what I'm about to do. I'm just going to show you a quicker way. This is called the eyeball method. Okay, so I have something to the 40th power. I just visually inspect this. I'm eyeballing it, and I'm saying, what's the derivative of x squared plus 3? The derivative of that is 2x, which is right there. So what is going to happen is the derivative is right there along with the dx. That's going to disappear, and I'm going to say, how do I take the antiderivative of something to the 40th power? It is something to the 41st power all over 41. That's going to disappear because this is the reverse chain rule. There's the answer. Okay, so a U substitution, you don't always have to say U equals something. At first you might want to do your problems like that. But there are a lot of problems that you can eyeball and get the answer. And that's why I'm telling you, don't rely on a table of new formulas, because that's only going to hurt you in your next calculus class. Because then, you're going to forget things from the tables. Let's do the next problem. I will be doing these problems both ways. So it's going to take a little longer to get through what I want to get through, but I think the other way is going to benefit people. Problem number 2. So the substitution rule is really the reverse chain rule. That is what it is. Let's do this problem. Okay, I have sine of x plus 9. I'm going to make a U substitution. Now sometimes it's not always obvious what to make U. I'm going to make U x plus 9. It's in the parentheses. So now I'm going to go ahead and say the derivative. Now you can write out du dx equals 1. I'm just going to say du equals, and then the derivative of x is 1, and then we put a dx. Okay, so this here, this dx is going to get replaced with the du. And I'm going to change to blue. We have the integral sine of u. And then we have du. So look, we're tricking this problem into getting done. Okay, let's continue. The antiderivative of sine happens to be the negative cosine. So I have negative cosine u, and then don't forget your plus c. Okay, I'm going back to the original problem because I don't want to leave my answers with u's in them. So this is going to go negative cosine of x plus 9 plus a c, and that completes the problem. So think of the substitution rule as you are tricking this problem into becoming a simpler problem. Let me go ahead and do this the other way. Okay, so this is, how about when I do things the other way? So I did things the other way. I'll go put a star by it to show you that we're done with the problem. I'm just showing you, some of you might want to become a little more efficient with integration. So here it is. The integral of the sine x plus 9 dx. Okay, so I look inside this parenthesis. The thing that I'm going to set u equal to, I don't write it all out. I say, oh, well, I have x plus 9 here. I'm doing the reverse chain rule. What's the derivative of x plus 9? It happens to be 1. And so I'll put a 1 right there. I don't really need to do that. And that, dx, and the 1 will disappear because I'm doing the reverse chain rule. So now I just have to say, what is the antiderivative of sine of something? It is negative cosine of something. The red part disappears, and because it is the reverse chain rule, and it's like the one disappearing, that's not as big of a deal as the last problem, and then you have to put your plus c. So look at this. I didn't have to write out any U substitution. So you might be asking yourself this question, well, Joe, why don't you just do the problems all like the purple way, like this way right here? Because there are going to be some times when I will write out a U substitution when things get more complicated in the integrand. Let's go ahead and do another problem. Next problem is the cosine 5x. So the cosine 5x, we've got to ask ourselves, well, we've never integrated the cosine of 5x. And it's because the argument of the cosine is a 5x instead of an x. So it would be great if it just said cosine of some letter like u. So let's make our u equal 5x. Okay. So du is the derivative of 5x, which is 5 dx. And now what we want to do is we see a dx there. We don't see a, we see this 5 here, but we don't see a 5 anywhere. So I'm going to divide both sides of this equation here by a 5. So I have du over 5 equals dx. Now I can get rid of the dx. So let's rewrite this problem. So it is the integral of the cosine, 5x is u, cosine u, du over 5. du over 5. Now, what I'm going to do with that, 1/5 is pull it out in front of the integral sign. I can do that. And then this is the cosine of u du. So all we have to do is know how to integrate the cosine of u. The integral of cosine of u is going to be sine of u. So this is going to be 1/5 sine u plus c. Now, lots of people want to box that answer, but remember our original question had x's in it. So I'm going to go ahead and replace the u with a 5x. So this is 1/5 sine 5x plus c. That completes the problem. Now, I'm going to go ahead and show you the eyeball method on this. The eyeball method. When I'm teaching differential equations, I will use the eyeball method a lot in that class, just because it's just more efficient. You can get the problems done faster. So I identify what I'd like my u to be, but I don't write it out. I say, well, look, 5x is what I want my u to be. What is the derivative of that 5x? Well, it's 5. And you might be thinking to yourself, well, you don't have a 5. Well, yes, I do. And then you might be saying, Joe, that's cheating. It is. You've now destroyed this problem, so you want to balance the books by putting a 1/5 out front. So now, it's like I have the same exact problem, and I realize because I'm doing the reverse chain rule that that's going to disappear along with that. And all I have to do is say, do I know how to find the antiderivative of the cosine? And I do. It's the sine. So it's sine of something. So this is going to be 1/5 sine of the something plus c. And in every one of these problems, when you get the answer, you could always take the derivative. The derivative of the sine is the cosine 5x, and then you have to do the chain rule, and then you get a 5, and the 5 and the 1/5 cancel, and you have the cosine 5x. So in every one of these problems, you can check yourself by taking the derivative of your answer. There will be some chain rule involved, and you should get the original problem. Let's go ahead and do another problem. You might want to just try to tackle this problem on your own, pausing the video and seeing if you can do that. Okay, so we got to make a U-substitution on this because this is pretty complicated. And the question is, what do we want to make U be? You know, some people might say, hey, we should make U be, I don't know, trying to see if I have, I'm seeing if I have the right problem here. I think I do have the right problem. Okay, so some of you might say, let's make U be the thing that's under the radical, and that's a good choice. I mean, some of you would say, well, let's make U be 5x squared, and when you go to do the du, you're not going to be able to get rid of this stuff. Okay, so let's go ahead and make U equal to the stuff that's under the radical. So I have x cubed minus 4 du is going to equal, I take the derivative, 3x squared dx. Now look what I have. I do have an x squared right there. There's a few ways of doing this. I don't have the 3 there, so remember on the other one I divided. So here's something fancy you can do. You could say, I'm just going to solve for dx and write this as du over 3x squared. Okay, and you can do it like that. Other teachers might say solve for x squared dx, and then x squared dx is du over 3. You're still going to get the same thing. I have to do it one way, so I'm going to do it this way. So when I go ahead and make the substitutions, I have 5x squared square root of u, and then I have dx, which is du over 3x squared. Now, we might be a little upset with this because there's x's and u's in here, but look what's happening to my x's. Those x's will cancel. Now, to prevent that, you could have just solved for x squared dx, which is du over 3, and not had that. But I'm willing to live with that. So this equals, we have a 5 and then a 3 on the bottom. I'm going to factor that out. So 5/3 times the integral of square root of u. I'm going to have to take the antiderivative, so I'm going to write it as u to the 1/2. And this is du. So can I do this problem? I think I can. I sound like the little train. I think I can. Great. This is going on YouTube. Okay, so 5/3. I'll take the antiderivative. This is going to be u to the 1/2 plus 1, which is 3/2. And then I'm going to put that on the bottom. Now I'm going to start doing something new. You know, lots of times I'll go like this and then put this on the bottom. This is going to happen quite often, where this happens often. And so what I like to do is I like to just jump to the next step, which would tell me to invert the bottom. So I'm going to put a 2/3 right there. You know, because you can do copy dot flip and you get that. So you might see me skip that step more often, and your future calculus teacher might do that as well. Especially if your future calculus teacher is me. Okay, so I have plus c. Let's go ahead and multiply those fractions together. That's 10/9, and I think I'll switch the u back. So let's just write out our final answer. This is 10/9, and then we have the u is x cubed minus 4. This is to the 3/2 power plus c. There's the answer. Once again, I'm going to do this the purple way, and some of you, this is where some of you are just going to fast forward the video. The purple way, see if we can do this. So this is 5x squared. We have x cubed minus 4 to the 1/2 dx. Okay, the purple way says take the derivative of this inside part. That's what I'm going to let u equal. So the derivative is 3x squared. And look what I have. I have a 5x squared. So I really want that right there. Okay. But now I've just messed everything up. I have to balance the books. So I'll put a 1/3 out front. This red part that I have inside the integral, the part of the integrand, that's going to disappear because it's the reverse chain rule. So the 5 will join the 1/3 out front. I'll have 5/3. And then the integral antiderivative of something to the 1/2 is the something to the 3/2 divided by 3/2 or multiplied by 2/3 plus c. And then I end up getting exactly the same answer, 10/9 x cubed minus 4 to the 3/2 plus c. So that is the answer. Once again, if you wanted to check your answer, I'll do this in green. Hopefully the green shows up all right. So here is a function, 10/9. We have x cubed minus 4 to the 3/2 plus c. Let's go ahead and take the derivative. So all I'm doing is checking my answer. The derivative happens to be, we'll just leave this right here, the chain rule. So something to the 3/2 power is 3/2. Then we go something, and then we subtract 1, we get 1/2. And then the chain rule says we take the derivative of the inside, which is a 3x squared. 3x squared. And that's done with this, and the derivative of c is 0. By the way, this is the part that disappeared. And when you do the chain rule the correct way, or you do the chain rule, it reappears. And so, wow, I have some reducing to do. I have these guys right here. The 3 and the 3 and the 9 will cancel out completely, and you'll have 10/2, which is 5. So 5, and then an x squared, and then this guy right here, which is the square root of x cubed minus 4, which happens to be, you can't see it, happens to be our original problem. Okay, one other thing that I want to say about this problem, and some of you are like, just leave this problem alone. So here was the problem right here, 5x squared, and then we had the square root of x cubed minus 4 dx. And remember when we did our u substitution, we let u equal x cubed minus 4. Whoops, I meant to pick up the blue one. Okay, well that was great. I'm going to show you that sometimes you could have more choices in terms of your u's. Okay, this is the one everybody would do, but I'm going to go ahead, and this is Math Gone Wild, volume 15. I'm going to let my u actually equal the square root of that. Now sometimes you'll let u equal something and there's nothing you can do. You can't, you run into a dead end, and then you have to re-evaluate and pick a different u. Watch what I'm going to do. I'm going to square both sides of this equation. So I have u squared equals x cubed minus 4. And then I'm going to take the derivative of both sides. So this is u squared. I'm going to go 2u du equals 3x squared dx. Okay. I'm going to go ahead and just solve for x squared dx. So x squared dx equals 2u du over 3. So here's the x squared dx. So I'm doing it this way this time. Going to replace everything. I wonder if I'll get the same answer that I got before. So this gives me integral 5. The orange part is going to become 2u du over 3. So this is 2u du over 3. So that's the orange part. And then this part right here is just what? It's just a u. So I'm going to pull the numbers out front. This gives me integral, I thought I was going to pull them out front, 10 thirds of u squared du. So let's integrate that. The integral of u squared is u cubed over 3. Then we have plus c. And this is really 10 ninths. Then we have u cubed. So here's u. It's this guy right here. Cubed. And I should have switched to black. Okay, this is plus c. And this right here, I mean, this is legitimate. This is a good answer, but I'm going to go ahead and just go a little bit further and write this as 10 ninths. This is x cubed minus 4, and then we have the square root. Roots grow underground, so that's going to be the denominator of that. 3 halves plus c. Now, whoops, okay. Am I saying when you do your homework you should do your problem 3 times? No. I'm just showing you that most people would do it the way we did it at first, where we said u equals x cubed minus 4, but we got the same answer. The purple way that I'm showing you right here is for the students who are like, oh, well, you know what, I'm going to keep taking calculus classes and technical classes, and I want to become more efficient. In Calculus 2, there's something called integration by parts, and a lot of the teachers will do the textbook method, but there is really a tabular method that is a lot faster. So when I do that, I will also have a quicker method. And sometimes those are what is needed because, you know, when you're out doing some technical work, you don't want to spend a lot of time bumping around with the U-substitution. Sometimes you need to do that when the problems are more difficult, and we will see a problem like that. Okay, let's go ahead and go do problem number 5. Problem number 5. Okay, so this is one of those where they didn't give you any of these in the book, but I put this on your antiderivative rule sheet. The antiderivative rule sheet for this, it's a b to the x. And the rule is you take the antiderivative, let's just say the integral, let's just put an I there. We take the integral of that, we get b to the x over the ln of b plus c. Okay, so that's just a rule that, you know, when we have the derivative of b to the x is b to the x times the ln of b, and so that's where we got the integration rule from. So let's remember that rule. I mean, let's just have that right here. It's usually the rule a lot of people forget. Let's see how the green is coming out. It's all right. So let's do a U-substitution on this one. What should we let u equal? Well, there's not really many things. I mean, I'm looking at this 3x plus 1 as a good U-substitution. Okay, so I'm going to say du equals 3 dx. And I have dx equaling du over 3. So there it is. I've been circling my dx's, or things that have dx's, with orange. Let's go ahead and write out the next step here. This is going to be 2 to the u, and then the dx is du over 3. Okay, I'm going to bring the 1/3 out in front of the integral sign there, and then we have 2 to the u du. Now, do I know how to take the antiderivative of 2 to the u? Well, it's just this rule right here. So I have 1/3, and then here it goes. This is 2 to the u divided by ln 2. And we'll put a plus c there. Okay, switching back to black, I'm going to replace that u with 3x plus 1. So it looks like I have 2 raised to the 3x plus 1 all over 3 times the ln of 2 plus c. There it is. Of course, your book would probably write ln of 8 on the bottom. Okay, that was a logarithm joke, and if you don't get it, then look at your properties of logarithms. So we're done with this problem. Once again, I'm going to show you the eyeball method, and some of you, really not big fans of the eyeball method, so move ahead on this video. The eyeball method says I kind of eyeball what I would make my u, and I would make my u equal to 3x plus 1. So what is the derivative of 3x plus 1? It is 3. And I just went ahead, and this is 3 times 2. It doesn't say 32. So I can't just put a 3 there. I have to balance the books by putting a 1/3 there. So this 3, this dx, because I'm doing the reverse chain rule, will disappear. And I'm going to write this 1/3, which is this guy right here. And then I remember the formula for the antiderivative of 2 to something. It is 2 to something all over the ln of 2. And this is plus c. And that's exactly, let me be a little lazy here, that's exactly what we got. So the eyeball method has worked on the first 5 problems. It will not always work, okay? Let's go ahead and do another problem. Problem number 6. So we've been doing 1 through 6 so far. We've just been doing these things called indefinite integrals, which means there are not numbers up there. We don't have limits of integrations. We will do definite integrals after we do a few of these and get comfortable with this. Now here is something that we do not have for antiderivative rules. We do not have the tangent on our list. We have the cosine and the sine, the secant squared, the cosecant squared. We have the secant tangent and the cosecant cotangent, but we do not have a tangent. We know how to take the derivative of this, but we've never taken the antiderivative. So this is going to be new. We're looking at this and we're like, what should we let our u equal? Should we let it equal x? That's a funny thing to do. If you let u equal x, then du equals dx, and you do all the substitution, your problem becomes tangent u du, and you're still in the same boat. So the only thing I can think of that might be useful is to rewrite the tangent in terms of sines and cosines. And if you remember your trig identities, the tangent is the sine over the cosine. Okay, so now I've got this, and I can try to set u equal to one of these things. What I'm going to do is I'm going to let u equal the sine of x and see what happens. U equals the sine of x, which would mean du equals the cosine of x dx. And that would then, I do see a cosine, but it's not right next to the dx. I have dx over cosine. So you might say, well, let's go ahead and go dx equals du over the cosine of x. And what will happen when you rewrite this is you will get the integral. You'll replace the sine with a u. You'll replace the dx with a du over the cosine x. And then you'll also have another cosine x on the bottom, which means you have a cosine squared x, which you did not get rid of the x's. Now you might say, I'm going to replace that with something, I'm going to use sine squared plus cosine squared equals 1, and you're going to get into a big mess. I'm not saying that you couldn't get the right answer out of this, but this is a lot of work. So I did this on purpose, and you also see I did it in red. I usually do my U substitutions in blue, But this just goes to prove that sometimes you might choose a u that will put you on a path to more work or a dead end, and you can't get rid of the x's, or if you can, there's going to be a lot more work. Let's see what happens if we had done the other choice of letting u equal the cosine of x. Well, then du, the derivative of cosine, is negative sine x dx. And look, that's exactly what you have on the top, almost exactly. There's a negative here, so let's just multiply both sides of this equation by a negative 1. And so look at this. This right here can be used. We have a sine x dx. That's out of there. That's going to become a negative du. And then you have u is cosine, and so you have a u on the bottom. So look what happens here. You have integral of negative 1 du all over u. Okay, so do we know how to take that antiderivative? Yes, this is going to be negative. I'll put the negative out front, and then this is u to the negative 1 du. And so the, oh, look, if I go to do the power rule, I replace that with a 0 and put a 0 on the bottom. So now I know that maybe I can't do that, and I have to remember the antiderivative of like 1 over x, which is the ln absolute value of x. So this is going to become minus ln the absolute value of u plus c. Let's go ahead and replace the u's with x's. And so this u is going to be replaced with a cosine x. This gives me negative ln absolute value cosine x. And then this is plus c. This is an acceptable answer. That's a good answer. Okay, so we're done with this problem. You can move on. I'm going to say a few things. I'm going to actually do it the eyeball method as well, but a few things to say. The first thing to say is you could, now some of you would say, why would you do this? Use the property of logarithms, the power rule for logarithms, and bring that negative 1 up top. So this would be ln absolute value cosine x to the negative 1. Now that negative 1 can come on the inside, and this is not the cosine inverse. This really is putting, in fact, I'll just keep the negative out there. I'm going to go ahead and put that on the bottom, so this says the ln absolute value of 1 over cosine x plus c. Now I'm going to use another rule of logarithms, the quotient rule, and I'm going to have the ln of the absolute value of 1 minus, oh no, I don't want to do that, then I'm going to get exactly what I got. Hold on. Some of you can see where that's going to lead me, and if not, then just ignore what I just said. I'm going to realize that 1 over cosine is the secant. So I have ln of the absolute value of the secant x plus c. I say this because sometimes books will give you a problem like this, and then you'll look up the answer and you'll see this instead of this, and you'll say, what happened? Now this for me is good enough. And this is, some teachers might, say, oh, well, this is better because it doesn't have a negative. But I like cosines better than the secants. Please don't tell other people that. So that is the first thing I wanted to say about that problem. The second thing I wanted to say is let's see if we can eyeball this one. So I'll do that in purple. The integral of the tangent x dx. So we'll eyeball this. What is this? This is the integral. So we still have to say this is going to be the sine of x over the cosine of x. Now sometimes when you have fractions and you're trying to decide on the u, it's always worthwhile to see if the bottom would be a good u and see if that would happen, and you would end up getting a natural log. So like I would set my sights on the bottom and say, well, what is the derivative of the bottom? The derivative of the bottom, the derivative of cosine, is negative sine. Look, I have a sine, but I'm going to need a negative. So I'm going to put a negative right there and a negative out front. That's going to disappear with the chain rule, the reverse chain rule. And so I'm going to say, do I know what the antiderivative of 1 over something is? It's the ln absolute value of that something. And that's exactly what I have right there. Okay, so you try, because now we can do another one that you didn't know about. You can try the integral of the cotangent x dx, and that will work out the same way. Can we integrate the secant of x and the cosecant of x? The answer is we cannot do that until the next class, because that's going to involve, I believe, integration by parts. It's going to involve something. And so U-substitution really does help us integrate things like the tangent of x. That is something that we couldn't have done until now. Let's go ahead and do a few more problems here. Problem number 7. So here's problem number 7. We have the integral of x to the 5th, the cube root of x cubed plus 1. So how am I going to do this problem? Well, I'm going to look for a good U-substitution, and the U-substitution could be u equals x cubed plus 1. So I'll write that in blue. U equals x cubed plus 1. Now, if I were doing the eyeball method on this one, I might actually stop, because the derivative of that is 3x squared, and I don't have like an x squared dx out here. I have a lot more x's than what this derivative does. So on a problem like this, I personally would not do the eyeball method. I would do it the way I'm doing it right here. So let's continue this. So du equals 3x squared dx. But here's the deal. We have an x squared dx equals du over 3. So we have this part taken care of. We have a dx there, and we do have an x squared there. So let's go ahead and rewrite this integral problem here. This is really the integral of x cubed times, let's put the x squared over here near the dx. So we agreed that this x to the 5th can be written like that. And then this right here is x cubed plus 1 to the 1/3 power. Okay, so this right here can get replaced with this. That right there is a u. So let me bring another color in, even though we weren't using colors for this. This might be a good idea. This takes care of that. The problem is there's an x cubed there, and we don't have anything, or do we? So sometimes when this happens and you have an extra x or something like that, you can go back to the original U-substitution thing and say, well, I can actually solve for x cubed. X cubed equals u minus 1. So this is a little bit more complicated of a U-substitution, because you have to do this extra part here. And so that will take care of it, but you got to admit that now that we have all those things that can turn into u's, that we're doing good. So let's go ahead and say the integral of u minus 1. Then what do we have here for the green part? We have u to the 1/3, and the orange part is du over 3. So So I'm going to bring the 1/3 out in front of the integral sign. I'm going to multiply that u to the 1/3 through, so I'll have u to the, let's see, that's going to give me 4/3 minus u to the 1/3. And now because there's two terms there, I'm going to put parentheses around this and go du. By the way, this guy right here is just one term. That's why I didn't put parentheses around there. And now I'm going to go ahead and integrate. So I have this 1/3 out front, and then I have u to the 7/3. 7/3 goes on the bottom, but I'm going to put, I'm actually going to put 3/7 there. And then I have minus u to the 4/3, 3/4. And then I have I'll just put the plus c out here. I'm going to multiply that through, so I have 1/7 u to the 7/3, and then the 3's cancel there, so this is going to give me minus 1/4 u to the 4/3, and then this is plus c. We've done all this work. We want to box that answer, but we've got to replace our u's. So when I replace my u's, I end up getting 1/7 x cubed plus 1 to the 7/3, and minus 1/4 x cubed plus 1 to the 4/3, and then I have plus c. And that completes the problem. If I went ahead and took the derivative of the thing that I just boxed, yes, it would be a lot of algebra and some chain rule and all that, and it would simplify to the integrand. So in terms of me doing this the eyeball method, no. I'm not going to do that, because I would actually just do it this way. Whenever the eyeball method is just so you can get some of the problems done really quickly, but this one, when I take its derivative, I don't have like just an x squared dx. If that x to the 5th was an x squared, yes, I would use the eyeball method. And then this could be something out here that when you go to do the U-substitution, you might end up not being able to figure out. They're not going to give you anything like that in your homework, but there are some problems where U-substitution just simply will not work, and then there's other techniques that you'll learn in the next class. Let's go ahead and do the next problem. Number 8. X to the 9th sine x to the 10th. Okay, so let's get one thing straight about this right here, because some people are going to get the wrong idea. Sine x to the 10th does not equal sine to the 10th. Okay, so this one right here really equals sine x raised to the 10th power, and this one right here is, well, sine x, that whole thing raised to the 10th, and then this is really the sine. This is x to the 10th as the argument of the sine. Okay, so those do not equal, so don't get the wrong idea here. And if you want, if it makes you feel more comfortable, put parentheses around the argument of the sine, but you don't need them when you're writing out the math. So the question is, what should we make our u? What should we make our u? Well, maybe we can make it what's inside the parentheses. U equals x to the 10th. Du equals 10 x to the 9th dx. And look, I have an x to the 9th dx. So x to the 9th dx equals du over 10. Now, on an earlier problem, I one time solved for dx, and then I would have put the x to the 9th on the bottom, and then I had an integral that had x's and u's in it. I'm going to try to maybe avoid doing that. It doesn't matter which way you do it, I just have to pick a way, and I feel like just doing it this way. So look what I have here. This is the orange part, and then I have a sine u. So this is going to be the integral of sine u du over 10. And this is, I think I stole one of these problems from the homework. This is, but it's like an even problem that I didn't assign. This is 1/10 integral sine u du, and this gives me, well, let's take the antiderivative of the sine. The antiderivative of the sine is negative cosine, so this is negative cosine u, and then we have plus c, and then I'll take this negative in front of the 1/10. This is going to be negative 1/10 cosine. U in this problem is x to the 10th. X to the 10th. You can put parentheses around that x to the 10th if you're feeling a little insecure. And then I have a plus c. That completes the problem. This one, I probably would eyeball it if I was just doing this on my own, because I have this right here. I have x to the 9th sine of x to the 10th dx. And so I would say, oh, look at this. The derivative of x to the 10th is 10x to the 9th. I have an x to the 9th. I need a 10x to the 9th. Balance the books by putting a 1/10 outside. That and that, those will disappear. And when I go ahead and integrate sine of something, I get negative cosine of that something. I'll put the negative right there, plus a c, and that gives me the same answer. So the eyeball method really does work. It's a good method if you like. Okay, we'll do one more indefinite integral, and then we'll do some definite integrals. So problem number 9 gives this right here. Okay, so this looks very complicated. And well, there is a formula. If you wanted to integrate something like 1 over 1 plus x squared, you take the integral of that, you end up getting the tangent inverse x plus c. So once again, this does not mean 1 over tangent. This is the, you know, some books would write that as the arctan. So that's not an exponent, it's just notation. Now, do we have that here? Do we have an x squared plus, you know, I mean, this looks really bad. Let's go ahead and do some things first. You know, we want to see if there is a U-substitution that we can do. I don't know. First things first, let's you know, if we're going to use this, the number on the bottom, you know, there's an x squared and there's a number. That number had better be a 1, and it's a 4 there. So what I'm going to do is I'm going to factor out a 4. So this is going to give me 9x squared plus 1. And then on the top we have dx. And really, if that upsets you, write a 1 on the top and put the dx over there. Okay, I'm going to factor that 1/4 out. And so I have dx all over 9x squared plus 1. Okay, so we almost have this form. And of course, the x squared's on the right side, and that's not going to be a big difference. But we would actually, we do have something squared here. So let me rewrite this so it says 1/4, and this is dx. I will put the 1 first. So I have 1 plus, and this is something squared. This is really something squared. It's 3x quantity squared. So maybe if we are trying to pick what you can be, what do you want to be when you grow up? Okay, u is 3x. And then this would tell you that du is 3dx. If you put u in for 3x, you will have the 1 over 1 plus x squared. I mean, there's the dx there. So dx equals du over 3. That's the one we've been circling in orange. And let's write out our integral. We have 1/4 And then we have the integral. dx is du over 3. I'll put the 3 over here. And then we have 1 plus u squared. So this is really 1/12, pulling that 1/3 out front, and then this is du over 1 plus u squared. And so when we keep going, this is going to be 1/12. This becomes the tangent inverse of u plus c. We're kind of running into this right here. And now it's time to replace the u's with 3 x's, and we have 1/12 tangent inverse 3x. It's one term, we don't need parentheses around it, but you can if you want, plus c. And so there is the problem. Now if I were going to eyeball this one, I would still do the same thing at the beginning and then say, oh look, I have a u here, and then I would put a 3 there and a 1/3 out there. And I'm not going to write the eyeball method on this one because I think some of you have been traumatized already enough. So that is problem number 9. Let's go ahead and do problem number 10. So now what's new on this? What is new is this is a definite integral. We have the integral from 1 to 5 of the square root 2x minus 1. We're finding a net area, and we're going to do a u-substitution. Now, let's go ahead and select our u. U is, we'll probably just select 2x minus 1. 2x minus 1. So du is going to equal 2 dx, and dx is going to equal du over 2. Okay, so that I should circle that in orange here. Now here's the deal. Let's rewrite the original problem, and I'm going to actually be a little more careful about this. When you have your limits of integration, this is really saying x equals 1, and this is x equals 5. That's really technically what we should write on our limits of integration, but we don't. I mean, this is legitimate shorthand, but that's really what it means. And so I'm reminding you of that so we can then do this problem here. I'll change the square root to the 1/2. And now, look what happens. When I change out my x's here, I should also change them out there. And you might be thinking, well, what do you mean? Watch this. If x is 1, and we plug it into this equation, what is u? U is going to be 2 minus 1. So u will be 1. Maybe that was a bad example. But okay, x is 5. I know this one's going to change. If x is 5, then I'm going to get 2 times 5, which is 10. 10 minus 1, so u will be 9. So my next integral says u equals 1 to u equals 9. U to the 1/2, and this guy right here is du over 2. Du over 2. Okay, I'm going to go ahead and bring the 1/2 out front. I'm going to just go 1 to 9, and then this is u to the 1/2 du. So this is 1/2 u to the 3/2, and then we're going to go 2/3 because we divide by 3/2. And this is now going to be evaluated from 1 to 9. Now evaluating it from 1 to 9, first of all, let's cancel the 2's. We have 1/3. And now, well, let's just write this out. 1/3 u to the 3/2. Evaluate it from 1 to 9. So when I put 9 in there, doing the fundamental theorem of calculus, I have 9 to the 3/2, then minus 1/3 1 to the 3 halves. Okay, so I have 1/3, 9 to the 3 halves. Well, this is really the square root of 9, which is 3, and then 3 cubed, which is 27. And then this one here is going to be, square root of 1 is 1, 1 cubed is 1. This is going to be 1/3. Now I can write this as 9 minus 1/3, or 27 thirds minus 1/3 happens to be 26 thirds. There's my final answer. And that could also be written as 8 and 2/3. Okay, both are legitimate answers. And this is one way of doing the definite integral with the U-substitution. This is the way that a lot of teachers will do it, and there are advantages of this way, changing these limits. The other way is not changing the limits, but doing the indefinite integral, finding out what the antiderivative is, and then going back to x's and then using these original x values. I'll go over that, but before I do that, when you have a change of variables, you know, this first integral right here, so let me go ahead and write that this is number 10. This first integral had x's in it, and it went from 1 to 5. This integral has u's in it, and it goes from 1 to 9. These are two very different functions here, and I'm going to show you those two functions. Here they are. So here's the original one, and we went from 1 to 5. I know that looks kind of small, so let me go ahead and say this is 1, this is 5. And then when we did our U substitution, we had a different function, which is square root of u over 2, which I'm treating as the x, and now we're going from 1 to 9. It just so happens it doesn't matter, you know, like which one of these you do when you're doing the definite integrals, you are going to get the same answer, which was 26 over 3 for the area here, or the net area, which is just the area, and then this area right here is also 26 over 3. So sometimes when you do change of variables, you distort the picture, and in the next, you know, when you keep taking calculus classes, you might learn how to change things into polar coordinates, and you then make the picture look a little different, but you're finding the same area. You do not have to do the pictures when you're doing your homework. Let me go ahead and do this problem the other way. So the other way with this problem, oh, now, is there an eyeball method for this? Not really, because I had to write out the u equal to x minus 1 to get these guys. So if I was trying to eyeball this one, I would kind of have a hard time doing that, because then I would have to change these in my head, and then I might end up messing that up. Let's go ahead and do this problem a way that some other teachers might do this problem, where we don't change the limits of integration to u values. So I have from 1 to 5. So this is just another way. And most of you will be happy with the first way. 1 to 5, and we have 2x minus 1 to the 1/2 power dx. Okay, so what I'm going to do is the same thing. You know what? I'll morph this other way. I don't know how to do this. I'll just do the U-substitution. Okay, so, and then I'm going to show you what some teachers might get some students on this. So this is u equals 2x minus 1, and then du equals 2dx, and then du, oh, so I'm doing the same thing pretty much. And so what I'm doing is I'm going to have u to the 1/2 du over 2, and there are some teachers out there that would really be upset if you kept the 1 and the 5 on the integral sign, even if you put x equals 1 and x equals 5, because in some ways this is not very pure. So some people might want to just do the integration without putting that, you know, so, I mean, if you're going to put them on, put x equals 1, x equals 5, but it's confusing because you're tempted to put a 1 and 5 into the u expression. So perhaps the best way to do this is not to write any of these and just figure out what the antiderivative of this is. So, you know, you could say, I'm just doing the antiderivative of this right here. And then you do this. So we have u, and we've done all this here. So this is u to the 3/2, 2/3, and there's a 1/2 there. This is plus c, and then we end up getting u to the 3/2 over 3, which gives you 2x minus 1 to the 3/2 over 3. So then you pop back out to this problem and you say, oh, I know what the antiderivative is. And I know on these ones there's a plus c and a plus c, but that plus c is going to go away when you do the definite integral. And so you have 2x minus 1 to the 3/2 power all over 3, evaluate it from 1 to 5. So there are some people out there who do not want to change this. Remember when we change it to 1 to 9, they just don't like doing that. They'll just go ahead and take the antiderivative and then come back to this problem, do this. Let's see if we get the same answer. I put 5 in for x, so I get 2 times 5, which is 10. 10 minus 1, which is 9. 9 to the 3/2 power, the square root of 9 is 3. 3 cubed is 27. So this is 27 over 3. You put 1 in there, you get 2 times 1 minus 1, which is 1. 1 to the 3/2 power is 1, so you get minus 1/3, which gives you 26 over 3, which is the same answer. So let's go ahead and do the worst thing that we could possibly do in a math lecture and do this problem again. You're saying, well, why are you doing it again? I will eyeball this one. So look at this. From 1 to 5, 2x minus 1 to the 1/2 dx. I know I'm going to eyeball this, and the derivative of the thing in the parentheses is 2. I need a 2 right here. I'm going to balance the books by putting a 1/2 there. The 2 here and the dx will disappear, and I'm going to take the antiderivative of 2x minus 1 to the 1/2 power. Something to the 1/2 power is going to be something. I'm taking the antiderivative to the 3/2 power. So this is going to be 2/3, and then there's a 1/2 out front. This gets evaluated from 1 to 5. This guy right here is going to become 1/3. I'll just keep the 1/3 out front when I do the evaluation. I put 5 in there. I get 10 minus 1, which is 9 to the 3/2. We already did that, 27. And then I put 1 in there, and I get minus 1, which gives me 26 over 3. Let's go do this problem a fourth way. I'm just kidding. So sometimes when I can eyeball a problem, I will actually just do the antiderivative and not change the limits, because for me that's a lot faster. But there's nothing wrong with any of these methods if you get 26 over 3. If you are going to do this middle method here, make sure that you're careful with other teachers. You might want to just say, I'm taking the indefinite integral, find out what the antiderivative is, and then pop back into the problem and then get the answer done. Because I've known the teachers to take off points even when you say x equals 1 here and x equals 5 there. Let's do another problem. Number 11. So with problem number 11, we want to do U-substitution, and you know, on these problems I will change my limits, you know, just so you can see that. That's going to be a way that a lot of people do it. Okay, so 11, I'm going to let U equal, well, probably the stuff in the parentheses. So I have U equals x squared plus 1, and du equals 2x dx. So let's go ahead and do this problem. You could also say, oh yeah, this is x equals 2, and instead of writing the whole problem again, I'll say that's x equals 2, and then this is x equals 0. Let's do our change of variables. So now, if x is 0, what is u? U is 1. And then if x is 2, u is going to be 2 squared plus 1, which is 5. Okay, I'm still not quite done here. I'm going to go x dx, which I definitely have here. This is great. X dx equals du over 2. So that's what I'm going to do with that. I'm going to, when I write the du, I'm going to put over 2, I'm going to put that right there. Okay, so this is, let me just circle this in a line here. And then what do I have right here? I have u to the third, u cubed. So the antiderivative of u cubed is u to the fourth over 4. And then this is going to be evaluated from 1 to 5. And so this is 1/8 u to the fourth evaluated from 1 to 5. I might have to go some big numbers here. 1/8. I'm going to just leave that out and then do the fundamental theorem of calculus just on the u to the fourth. So I have 5 to the fourth, which is 625, minus 1 to the fourth. So this is 624 over 8. 624 divided by 8 gives me a nice 78 for my answer. And so there it is, a U substitution when you have a definite integral. I will go ahead and do this. I know this is making the video a lot longer. I'm going to go ahead and do the eyeball method here. So I have 0 to 2 x squared plus 1 cubed dx. The derivative of the inside there is 2x. I need a 2 there, so that will disappear, but I need a 1/2 there. So I end up getting 1/2, and I'm taking the antiderivative of something to the third, which is something to the fourth over 4. And this is going to get evaluated from 0 to 2. So I have a 1/8 out front. I put a 2 in there. I get 2 squared plus 1, which is 5. We have 5 to the fourth. You can kind of see the same thing happening there. And then I put a 0 in there. I have 1 to the fourth. So this is minus 1 to the fourth. And we have 1/8 times 624, because this is 625 minus 1. So that's 624 over 8, which gives me the same answer. So once again, this is just if you were going to try to eyeball this one, then you don't really even have to change the limits of integration. But changing the limits of integration does have its advantages, and it will help when you are doing multivariable calculus, because sometimes you just must change those limits of integration. Let's go ahead and do another problem. So how many problems am I planning on doing? I'm planning on doing 16 problems, and I know that's a lot of problems, but the more you see me do, maybe the more confidence you have when you go to do your homework. What should we let u equal in this case? Well, why don't we let it equal that exponent? U equals x squared minus 1. du equals 2x dx. Look at this. I have an x dx right here. So I'm going to say x dx equals du over 2. Let's go ahead and do this problem here. We have, this is x equals 1, and this is x equals 2 here. So when x is 1, u is going to be 1 squared minus 1. That u is going to be 0. And when x is 2, you have 2 squared, which is 4. 4 minus 1 is 3. Okay, then we have the orange part becoming a du over 2. So that's what the orange part became. And then we have e to the u. So we have 1/2, antiderivative of e to the u is e to the u. This gets evaluated from 0 to 3. 1/2, and then let's go ahead and put parentheses up. We'll put a 3 in there. So I mean, we can go like this and say, let's evaluate that from 0 to 3. This is going to be e to the 3rd minus e to the 0. And so it looks like we can write this as 1/2 e cubed minus 1. Now, because I want to get through these problems, if you want to try to do it using the eyeball method, you can. How much time do I have? 20? Yeah, I'm going to do it. Okay, so for those of you who are like, yeah, I hate when he does it, and you can forward to the next problem. So this is from 1 to 2, x e to the x squared minus 1 dx. By eyeballing this, I see that the derivative of that exponent is 2x. I need a 2x dx. So I put a 1/2 out front. The red part on the inside is going to disappear. I'm going to get 1/2. The integral of e to the something is e to the something. Evaluate it from 1 to 2. Okay, so I have 1/2. I put 2 in there. I get 2 squared minus 1. So I kind of did that calculation to get those guys, didn't I? Which is 3. So this is e cubed minus. And then I put 1 in there. I get e to the 0, which gives me the same answer. Let's go ahead and do the next problem here. Problem number 13. Some of you are going to love this because it has trigonometry in it. Okay, so this is a weird one. I'm integrating cosine x times the sine of the sine x. So that's really weird. I don't like that there. So what we want to do is maybe set our u equal to the sine x. So du is going to be the derivative of the sine x, which is the cosine of x dx. And what I have that right there. Cosine x dx is just sitting right there. We're ready to do our substitution. This is x equals pi halves. This is x equals 0. Let's change everything to u's. What is the sine of x? Sine of 0? Sine of 0 is 0. So that's u equals 0. And the sine of pi halves. So pi halves, that's when the sine... So I'm thinking of the sine graph, which goes like this. Some of you are just like using your calculator to figure this out. What I'm going to end up getting is the value of 1. So u equals 0 to u equals 1. The orange part becomes a du. And the other part is the sine of the sine x. So this is the sine of u. Okay, now I'm going to go ahead and take the antiderivative of the sine, which is negative cosine. This gets evaluated from 0 to 1. So I put 1 into this function. I get the cosine of 1. Actually, I get negative cosine of 1 because negative is part of the function. And then I'm going to go ahead and put 0 in there, and I'm going to get negative cosine 0. So this is negative cosine 1. I don't know what that is. That's just the number 1. So if I didn't have a calculator or I had to put an exact answer, I would keep it like this. And then this is the cosine of 0 is 1. So this is minus negative 1. So this is really just a positive 1 there. So your final answer is going to be 1 minus the cosine of 1. And this time I will not do the eyeball method, but if you eyeballed this one, you would get exactly the same answer. Let's go ahead and do problem number 14, another problem that I took from an even problem from the homework. Here it is. Somehow I can't grip the paper. What's wrong with me? Okay, so I have this right here. Wow, what am I going to do for this problem? Well, I've got to set u equal to something. Now, I have a cosine cubed. Okay, that's a cosine theta in parentheses with a cube on it. So perhaps, maybe the u could be cosine theta. du is the derivative of the cosine, which is going to be negative sine theta d theta. I'm going to make sure the camera's still on. It is. And it looks like I have negative du equals sine theta d theta. So this guy right here, it's that guy right there, and then you have a u cubed on the bottom. These guys are theta values. Theta equals pi fourths. Theta equals 0. Let's see if we can change everything to u's. Okay, what is the cosine of 0? The cosine of 0 is 1. What is the cosine of pi over 4? Well, pi over 4 is a 45-degree triangle, 45, 45, 90. And so that's going to be 1 over the square root of 2. Okay, the orange part becomes du. Actually becomes negative du. Put that negative out in front. And then what do we have here? We have 1 over cosine cubed, or u cubed. So let's go ahead and continue. This is these are u values now, 1 up to 1 over root 2. This is u to the negative 3. I did that on, so we can do the power rule a little better. So this is negative. Okay, this is going to be u to the negative 2 divided by negative 2. This gets evaluated from 1 to the square, 1 over root 2. The negatives are out of there, so I'm going to go ahead and bring the 1/2 out, and then this is going to be just, let's fix this up too. This is going to be 1 over u squared, and we'll just go like that. That's going to get evaluated from 1 to 1 over root 2. Okay, so this is 1/2. I'm going to put 1 over root 2 into here. And when I do, I end up getting, so this is going to be like 1 over, and then this is squared, so it's going to be 1 over 2. I'm going to copy dot flip. This is going to be 1 over 1 times 2 over 1. So the first one I'm going to get is going to be a 2. Okay, so yeah, I'm plugging 1 over root 2 in there, and it's in the denominator. I kind of did some work in this cloud over here. That represents my brain, or I don't know what it represents. And then I put 1 into this function, and I just get a 1. And then the fundamental theorem of calculus says we subtract. And we end up getting 2 minus 1, which is 1. 1 times 1/2 is 1/2. That completes problem 14. Okay, once again, you could eyeball this one, but I think I'll just keep doing the problems this way, because this is the way the majority of the teachers do it. And, in terms of this isn't so bad. Sometimes changing those limits of integration is good, because you don't have to worry about changing everything back to x's. Go ahead and do problem number 15. Here it is. And so on problem number 15, I've got this big mess of a problem. And let's go ahead and make our u be 1 plus 2x. U equals 1 plus 2x. So du is going to equal 2 dx. Okay, so dx is going to equal du over 2. So got that right there, and that right there. Now, there's an extra x there, so we're probably a little nervous about that. So maybe we did the wrong substitution, I don't know. Could I get rid of that x? I probably can by doing the following. So first of all, here's green, this. We've got that covered. It's this extra x that we're all worried about. And so sometimes with the so this one I would not eyeball at all, because whenever, eyeballing it, I would just say, what's the derivative of that? Oh, it's 2. Do I have a 2 on the top? I can put a 2 on the top by putting a 1/2 there, but I don't, there's an extra x there, and that makes me extra nervous when I want to do things in my head. So this is how I would do the problem. Now, what we're going to do is we're going to solve for x here. So 2x equals u minus 1. X equals u minus 1 over 2. So it does look like I could solve for x. Now my limits of integration are written in terms of x's. This is x equals 0, x equals 4. I'm going to go ahead and see what happens. When x is 0, u is 1 plus 0, so u is 1. And when x is 4, we end up getting 1 plus 8, which is 9. So now this integral is going from 1 to 9. The brown part becomes u minus 1. And then you have, I'll just put the 1/2 out front and say, okay, there's the brown part right there. The orange part becomes, let's put parentheses around that. This is du over 2. I'll put that 1/2 out in front as well. Okay, so that's what the orange part became. And then the green part becomes, this is all over the square root of u, which is really u to the 1/2. And maybe at first glance you're thinking to yourself, we just made this integral worse. It does look pretty bad. Look what we can do here. We have a 1/4 out front, integral from 1 to 9. And what I can do with u minus 1 over u to the 1/2 is split the fraction. And that's going to help me get this problem done. Okay, so I have 1/4 out front, integral from 1 to 9. U to the 1/2 is the first one, and the second one is minus u to the negative 1/2 du. Okay, so I have 1/4. I'm going to integrate u to the 3/2, 2/3. And then the next one's going to be minus u to the, I'm adding 1 to those exponents, 1/2. And then this is going to be 2, I guess, over 1. And then this gets evaluated from 1 to 9. Another piece of paper. So what I'm going to do is I'm going to factor a 2 out of the top. So this is going to become 2/4. And here I have u to the 3/2 over 3 minus u to the 1/2. 1 to 9. Okay, we'll continue. On the outside we have 1/2. I'll just put a really big bracket here. Now I'm going to put 9 into this. So if I put 9 into this, because I'm doing the fundamental theorem of calculus, I get the square root of 9, which is 3. 3 cubed is 27. 27 over 3 is 9. Wow. So plug 9 in there, you get 9 out. And then this is minus square root of 9, which is 3. So that's putting 9 into that function. Now I'm going to put 1 into that function. I end up getting 1/3, because 1 to the 3/2 is 1. And then minus square root of 1, that's 1. Okay, wow, this is all just arithmetic now. We have 1/2. And then what do we have here? We have 9 minus 3, which is 6, minus 1/3 plus 1. So this is 7 minus 1/3, which is 7 is 21 over 3 minus 1/3. Gee, I sure hope I'm going to get the right answer. This is 1/2. This is 20 over 3 And then the 20 and the 2 can cancel, and you end up getting a 10 on the top and a 3 on the bottom. So 10/3 is the answer. Whew, that was quite intense. What made this one more intense, it wasn't just straight u equals du equals. You also had to solve for the x, and we ended up getting 10/3. I would not use the eyeball method on this one. Let's go ahead and do our very last problem of this section, which is this one right here. It's sine squared. So there's a last grouping of problems where they have sine squareds or cosine squareds in them, and this is something that comes up in differential equations. And I guess what they want you to remember is that the sine squared theta is actually 1 minus, this is a trig identity, 1 minus cosine 2 theta all over 2. So if we're going to integrate this, we're really going to want to integrate from 0 to pi over 4, and we have 1 minus cosine 2 theta all over 2 d theta. Okay, so what do we have here? We have the integral from 0 to pi fourths. This is really like 1/2 minus 1/2 cosine 2 theta. You can hear one of the neighbors using a circular saw. So this is probably a good time to have the last problem. And what are we going to do now? Well, what we're going to do now is we are going to do a U-substitution. What should we let U equal? Well, you could let U equal 2 theta. I would probably just eyeball the rest of this problem and then keep those, but I'm going to go ahead and let U equal 2 theta. And then what does du equal? Du equals 2 d theta. So d theta is going to equal du over 2. So let's see what we have when we do that. I'll switch it all over to blue. These are x values, or actually theta values. So if theta is 0, then u is going to be 0. And if theta is pi over 4, then u is going to be 2 times that, which is pi over 4 times 2, or pi over 2. And then what do we have? We have 1/2 minus 1/2 cosine u. We have a du, or it's a d theta, which becomes a du over 2, so this is du. And then this is over 2, which is right here. We'll put that right there. My equal sign's a little high on that one. Oh well. So this is 1/2. Actually, let's factor out a 1/2. So this is going to be 1/4 integral from 0 to pi over 2. And then this is 1 minus cosine u. This is d theta. Or du. What am I saying? So this is 1/4. And now the antiderivative of 1 is u. And the antiderivative of negative cosine u is negative sine u. This gets evaluated from 0 to pi halves. Okay, so I have 1/4. Let's go ahead and put pi halves in, and we end up getting pi halves, because that's u, and then we have sine of pi halves. Sine of pi halves is, let me just write that down, minus sine pi halves. Okay, that's the first part, and the second part of the fundamental theorem of calculus is putting 0 in, so I end up getting 0 minus sine 0. Oh man, I'm losing it here. Oh wait, what am I doing? I just plugged those values in. I don't know what that is there, by the way, okay? So for all you environmentalists, I'm going to not waste another piece of paper on this. So we have 1/4, and then in here we have pi halves. What is this? Minus sine of pi halves. Sine of pi halves is 1. So this is going to be minus 1. And so this gives me pi over 8 minus 1/4, which is good enough for the answer. There's the exact answer. You don't want to plug this into your calculator unless they tell you to round to something on a test. Some books might say this is pi minus 2 over 8 because they got a common denominator. This is good enough. And now you've learned substitution method, or change of variables, and this is gonna you're gonna see this all through the next calculus, and you're gonna see this big time in calculus 3, where you start having double integrals and you're changing variables to polar coordinates and to other things as well. Keep up with your homework, study hard, have a good day.